Let's remember what the fundamental theorem of calculus says. The fundamental theorem of calculus says that if I take an integral from a to b of the derivative of some function, we get the difference between f of b minus f of a. So this is the tool we use to calculate integrals. It means that finding antiderivatives is a critical part of doing calculus and doing single variable integrals. So it's absolutely important for everything we've done so far. The fundamental theorem of calculus for line integrals is very similar to this. And what it does is it says, if we've got a vector field and we do a line integral on it, if we knew that that function was a gradient of something, then I can calculate the line integral using the anti-gradient. So if I've got a curve and it starts at a point P and it goes along some path and it ends at a point Q, and I want to calculate the line integral of a gradient vector field, I can calculate that by just taking the anti-gradient, f, and taking the difference between the end point and the start point. This value, f, is sometimes called an anti-gradient, or sometimes it's called a potential function. It measures potential energy, and our total change in energy is measured by taking the difference between our potential energy at the end and our potential energy at the start. That's the kind of situation that we have where we can apply the fundamental theorem for line integrals. So for example, here are three vector fields. The first one is f of xy is 0, negative 9.81. That function has an anti-gradient. This function I've written at the right, negative 9.81 times y, is a function so that if I take its gradient, the x derivative is 0 and the y derivative is negative 9.81. And so that gives me that this vector field is a gradient vector field. This function x comma y also has an anti-gradient. The anti-gradient is x squared plus y squared equals 2. And this function over here is also one that has an anti-gradient. You can check that if I take the gradient of this function on the right, I get this vector field on the left. So all of these are kind of important. This one and this one on the top and the bottom one are related to gravitation. The top one is gravity on Earth, and the bottom one is kind of gravity pulling towards a central mass of some type. So most of the functions that we see in calculus, the reason that we can use the fundamental theorem of calculus so often is that most functions have an antiderivative, so we can do integrals. But in higher dimensions, this is not true. Most of the time, if I write down a random vector field, it's not conservative. It doesn't have an anti-gradient because it doesn't have this property that integrals only depend on where we start and where we end. That's very, very special, and conservative vector fields are very special types of vector fields. So if we have an anti-gradient, it's called a conservative vector field.